Good evening, ladies and gentlemen. I'd like to welcome you all here for this evening's edition of the von Kármán Lecture Series. Hope you can hear me okay out there. Let's just jump right in, shall we? The Mars Reconnaissance Orbiter arrived at the Red Planet on March 10th, 2006, and after an aerobraking phase began its primary science mission in November of that year. Equipped with a sophisticated suite of instruments and orbiting at a lower altitude than any previous Mars orbiter, MRO has already begun to provide us with unprecedented views of Mars. Tonight we'll see and hear about some of those early results. Tonight's speaker is the Deputy Project Scientist for the Mars Reconnaissance Orbiter, where she helps coordinate the efforts of dozens of researchers working on the mission's 8 scientific investigations. She received her bachelor's degree in geophysics and math from Brown University in 1984 and her PhD in geophysics from Southern Methodist University in 1990. Following a postdoc position at the Massachusetts Institute of Technology, she came here to NASA's Jet Propulsion Laboratory in 1992. At JPL, her research focuses on tectonic processes and interior convection, particularly for Mars and Venus. She has over 10 years of experience on a wide variety of missions, holding positions covering all aspects and phases, from science definition teams to data analysis and archiving, to instrument teams to project scientist. She has also authored numerous papers and received a variety of awards. Ladies and gentlemen, please join me in welcoming tonight's speaker, Dr. Sue Smrekar.
All right. Well, good evening. It's always a fun time to come out and talk to people interested in Mars. So I'm happy to be here tonight. And especially so given that MRO has already collected just 4 months of data, and I think you'll agree that it's beautiful data. It's really gorgeous. So hopefully this talk will practically give itself. As you heard, I'm the Deputy Project Scientist. Rich Zurek is the Project Scientist. He's here tonight, and we'll be giving the talk tomorrow night at PCC. I'm the geology part of the operation, and Rich is the atmospheric part. So if you have questions on the end, I'll probably refer you to Rich. So I'm going to go ahead and get started here. Okay, this is a very quick outline of what I'm going to talk to you about. Why study Mars? You probably are already pretty familiar with that, but I'll give you a very brief intro. And why another Mars orbiter? Why Mars Reconnaissance Orbiter? I think it'll become clear through the talk, but a few of the key things are the resolution. We're getting much higher resolution than we had before, in part due to the instrument design, in part due to our lower altitude. To bring back that higher resolution information, we need much more data volume, and as you'll see, we have that in spades. We also have a very helpful feature in that our ground track repeat comes around every 17 days, and our spacecraft is able to roll off in either direction to look at different parts of Mars. So the result is that we can look at an area on Mars, pretty much anywhere, any area, within 17 days. And as you see, we're looking at a number of variable phenomena, seasonal phenomena, and it's great to be able to just go back and look at sites right away. Okay, so then as the title advertised, I'll talk about some new perspectives on early Mars and Mars today that we've gotten already from MRO data, and just some cool stuff that I wanted to throw in. Okay, so here's a brief motivation for studying Mars. Probably one of the most captivating ones is the fact that life could have developed on Mars. Of all the planets in the solar system, it's the most Earth-like in terms of its climate. It has an atmosphere, has a solid surface. It's close enough to the sun so that it could, perhaps does, have liquid water. In general, the conditions on Mars are such that water only exists as ice and vapor in the atmosphere. As you'll see, there's some possible evidence for at least transient, quick liquid water. And so as a place that has liquid water, it's a place where life might have developed. And if life didn't develop, that's also an interesting question as to why on Earth but not on Mars. In addition, climate change is a big topic, as we all know, for Earth right now. And Mars has also experienced very dramatic changes in climate over time. Oh, this is going to be a problem, I think. Okay, so early in its history, water carved giant channels in the surface, and it left minerals behind. So we know that early, and when I say early, I mean the first billion years of Mars history, water was abundant. But today, the planet's surface is cold, its atmosphere is thin. What happened to that large volume of water that used to be present on Mars? Another reason that Mars is captivating is that it's a possible destination. It's Earth-like in that it has seasons, day-night cycle. It certainly has at least some limited water resources and others that could be used to sustain human presence. And its environment is such that it's possible for humans to stay and work there. Okay, so we can sum up one of the big questions in Mars science with this title, Got Water? And this will be a theme tonight. The answer is yes and no. We know that water is present in the ice caps, it's present in the atmosphere, and that there's at least a thin layer in the soil, the regolith near the poles. But in comparison to the amount of water that occurred early in the history of Mars, that's just a thin layer. So we know, some of the questions we'd like to answer are, early in the history of Mars, how long did the water persist on the surface? We think in order for life to evolve, you need to have water present for long durations. It can't just be a transient event. There's some evidence that there was once an ocean, and we'd like to investigate that question further. Now, the leading hypotheses on what happened to the early water are that it was either lost to space. Mars does not have a strong magnetic field. It has no interior magnetic field right now. And early on, it probably had a dynamo and a magnetic field, but it didn't last for that long. So the solar wind is able to erode water and other molecules off the top of the atmosphere. So it may be that it was once a thicker, warmer atmosphere that allowed the water to erode off the top, or it may be that it's simply frozen underground today, and that's one of the questions we're trying to answer. Okay, a few facts about MRO. I really don't know why I was doing it that quickly like that. Okay, so our primary mission is there actually, I don't think I have a pointer up here. If there is, I don't know where it is. Well, I'll use my arrow. Our initial mission is meant to last 4 Earth years. Our first 2 years are spent doing science with some relay of other data from other missions, plus 2 years where our primary role is to relay data from landed missions, and I'm sure we'll be trying to take some science data in that time as well. We have an international payload. We have imaging at both the scale of meters and at the scale of at basically 6 meters a pixel, where that's about 18 feet, and hyperspectral imaging, which we use to understand the composition of the surface, atmospheric profiling and weather monitoring to understand how water and dust are cycled through the atmosphere. The radar probes underneath the surface down to a depth of 1/2 kilometer or more in ice, and we get a higher resolution gravity field as well. We have a couple of technology payloads. There's an optical navigation camera, which was used, thank you, during the approach to Mars. And the objective for this is to be able to land very precisely for future missions, for landers, or perhaps eventually for putting people on the surface. We also have another radio experiment, the Ka band, which is able to send back very large volumes of data. So that was an early experiment. And I think you've heard some of these dates already. Our mission started in early November. The science, we have a broad range of science objectives that we're trying to address. We're going to characterize the seasonal cycles and daily cycles of water, dust, and carbon dioxide in the atmosphere. We're going to look at the global atmospheric structure, transport, and surface changes that reflect the seasonal changes. We'll be looking for evidence of aqueous and hydrothermal activity, basically looking for minerals that formed in the presence of water. We'll characterize the stratigraphy, geology, and composition of a variety of Mars surface features, We're going to look at the ice caps and the polar layered terrain. They're records of climate change. With the radar, we'll probe the upper crust and subsurface, looking for water and ground ice. And with the gravity field, with the new gravity field, we'll look at the interior of Mars and the upper atmosphere in greater detail. And one of our main objectives is to find sites that will be the locations for future landers. Okay, so I want to take just a minute to talk about where MRO fits into the Mars program. The suite of operating spacecraft at Mars are shown here. There are two orbiters from the US, Mars Odyssey and MRO. There's the European Mars Express mission, and of course the two rovers, which are still going on the surface. As you can see, the plan in the US is primarily to, sorry?
Can you please turn off the lights?
Oh. Lights, please? Thanks. The strategy in the US is to have alternating orbiters and landed missions. Here we had rovers. The next mission is going to be a lander that'll go to high latitudes where we think there's ice in the soil. And as you'll see, it's extremely beneficial to have both orbiters and landers or rovers on the surface. And the reason is that with orbiters, we can pick exciting places for these landed missions to go. The landed missions give us ground truth. We have something that's actually making measurements directly, closely on the surface that help us interpret our data that we take from orbit. And we're already providing new data to help the rovers chart their course, and I'm sure we'll be doing the same for future rovers as well. So together, these parts are greater than a single mission. The return is much enhanced by having a whole suite of missions at Mars. Okay, so I'm not going to go through all these. These are the people providing these instruments and their locations. What I want to draw your attention to are our suite of instruments, and I'll just go through these, getting you familiar with the names of these instruments. CRISM is our imaging spectrometer. It takes data in two modes, high resolution and survey, and this is our spectrometer that tells us about the composition. The high resolution camera is HiRISE. It only takes very high resolution data, small chunks, and one thing to remember is that even though we expect to return thousands and thousands of high-res images, we only expect to see about 1% of the surface of Mars. So high resolution, but a small area. To help out with that, we have some other cameras that will also be taking data for larger regions. SHARAD is our radar that will be taking high resolution and survey data for Mars. The context camera is very helpful in that its swath is 30 kilometers across. HiRISE is only 6 kilometers. So it provides, it sort of extends the coverage out so we can see interesting features, how far they trace out into the surrounding regions. This is our 6 meter per pixel. HiRISE has 25 centimeters per pixel, up to 30 centimeters per pixel in the images. So, it would be easy enough to, it's certainly easy enough to see a rover on the surface. It's easy enough to see a couple people sitting together on the surface. So it can really see very tiny things on the surface. We have Marcy, which is a very broad angle camera. It takes a daily global image of the surface, and it's really aimed at looking at clouds and dust storms and seasonal changes on the surface. The Mars Climate Sounder is constantly monitoring the atmosphere, seeing how the temperature changes, how the dust content is changing. The accelerometer was active in the first part of our mission, basically when we were aerobraking and getting closer to the surface of Mars. The accelerometer was telling us the density of the atmosphere as we were going through it, and so that experiment only operated very early on, but it's told us a lot about how the density has changed at different seasons on Mars. And gravity science is conducted using the Doppler data from the radio tracking. And just the changes in density in the interior of the planet actually cause a Doppler shift in the radio signal. So we are actually able to monitor the density in the interior of the planet just from looking at the Doppler data. Okay, so this takes a little bit of time to come up. It's the family portrait. You get a sense of the scale of high-rise. This person standing here, you can see it's essentially a flying telescope. This is Marcy, the wide-angle camera. These taco shells give it the wide field of view. This is the Chrism spectrometer, which gimbals about this axis and allowing it to look at more of the atmosphere as it takes an image. This is the Schrad antenna. Here's the undeployed radar antenna. It's actually 10 meters across when it's unfurled, and their electronics box is up here. This is the Mars Climate Sounder. It has 2 sets of sensors, and the context camera. Okay, so I said one of the ways we get our resolution is through low altitude, and our orbiter is actually flying at about over 100 kilometers lower than past spacecraft, so about 60 miles lower. And that really helps us out in terms of seeing high-resolution images on Mars. This is a quick comparison of our instruments versus some of those on past Mars missions in the visible through thermal parts of the spectrum. The instruments on the Mars Global Surveyor are shown in yellow, and unfortunately, Mars Global Surveyor, after over 10 years of operating at Mars, has met its demise. So these instruments are no longer working at Mars. The gray instruments show those on the European Mars Express mission, and blue is the Mars Odyssey mission, which is still alive and healthy. So here's where MRO fits in. And Marcy, the wide-angle camera, is meant to take data in a similar scale as the prior camera, and that's so it can continue its observation of the same sort of atmospheric phenomenon. The spectrometer is taking data at much higher resolution, almost an order of magnitude for the targeted images. And you can see our context camera on some missions might have been their high-resolution camera, but here it's our medium resolution. And for high-rise, it's the highest resolution orbital camera so far. Okay, to get that data back, we need lots of data volume. And we expect to return 3 times as much data as these 5 prior and current missions put together. And as of about 2 weeks ago, we'd already returned 7 terabits of data. And so if you've ever gone from having a modem at home to having DSL, that's what you're talking about right here. It's like having DSL coming back from Mars for us. So it's been a great leap, and it's really hugely helpful. Okay, so now I'm going to talk about old Mars, and what I'm really talking about here is the first billion years of its history. On Earth, that entire part of our history has been erased. It's been recycled back into the interior through plate tectonics. But on Mars, that very early history is preserved. And some of the things we're going to look at are evidence for oceans, for lakes and rivers, particularly layers deposited in water. And we'll look at the layers in terms of just their geologic context. But another aspect that's important in terms of understanding the history of water in these layers is their composition. So we'll also be looking at areas where the minerals are telling us that water was present for a substantial amount of time. We also want to know, was there water underground? And we'll look at some evidence for that. Okay, so was there an ocean? Some data points to that. This is a topography map which shows the North Pole, and those black lines are areas that people have mapped as possible ocean shorelines. This has been a controversial issue. Some people feel the evidence is clear. Some people question whether that ever really existed. Some things we do know are that the surface layer, the material that covers the northern plains, buries craters. If these are ocean sediments, what we would expect would be to have fine-grained sediments there, except for perhaps boulders that might have been rafted in on ice sheets, ice flows. But the bottom of the ocean, in general, the sediments are very fine-grained. Now, the presence of meter-scale rocks would be more consistent with deposition by floods or glaciers. So this is a high-rise image of that area, and high-rise has taken actually hundreds of images of this area, of the northern plains in general. Here's another image. These scallop-like features are believed to form as water or ice sublimates away, leaving these kind of bathtub rings. If we zoom in on that little square, this is what it looks like. Each of these little circular or these little dots, what I should say, are in fact large-scale boulders. And in helping the Phoenix lander look for a landing site, HiRISE has taken over 150 images in this northern plains area, and they are rocky in all the HiRISE images. So what that suggests then is that it is most likely not a simple ocean basin with fine-grained sediments. There probably was some help from glaciers of some kind or dropping these boulders, but even so, it's not what you would expect from a typical glacier. Usually glaciers pile up their boulders in a particular pattern. They dump them at the end. They usually leave boulders beneath them. So this isn't a typical distribution of rocks just put down by glaciers. So it's really still a mystery what caused all these sediments to form in the northern plains and how was water related to those processes. So we're just starting to learn more about that question, and I'm sure we'll have some new surprises in that area as well. Okay, so I also said I would talk about layers that are most likely formed in water. On the right, at the bottom, there's a delta formation. So it looks like something that you would see at the mouth of a river. Many different flows have come out and deposited their sediments. And here's a zoom in on part of this area. You can see these beautiful layers persisting over many kilometers. This is a single high-rise image, so each one is 6 kilometers across. And I'll be showing you some zooms on some of these as well, but typically they're at least 6 kilometers across, maybe less. And there are many, many such features on Mars. It's not always easy to tell, though, how these layers formed. There's a variety of ways in which deposits can form. Obviously, these layers were water deposited, but in some places you just see layers and you don't really have the same kind of evidence you have here for them being deposited in water. They could be lava flow layers. They could be layers of sand that gets deposited by wind. They could be layers of volcanic ash that's deposited by wind. So in some places we have good evidence that the layers are deposited in water. In others, it's more of an open question. Here's another example of some of the beautiful layers that HiRISE has seen. And a number of these places that I'm going to show you are candidates for locations of future landers, the next generation of rovers. We're currently starting to survey a series of sites that people have proposed as scientifically interesting and good locations to go to. Almost all of them are layer deposits like this, where they hope to go and investigate the past history of water. And one of the things that the data that we're collecting is going to be used for is to try to determine, is there good evidence that these are actually deposited in water, or could they have formed in some other manner? And here's a side of, I believe it's Melis Chasma. You can see lots of layers exposed as the surface here. We're going to zoom in at the top of the canyon wall right here. And what you see, in fact, in this area is that these are not deposited by water. These show evidence of cross-bedding. See how different layers come up and terminate against this long continuous layer. It's a very distinctive bed form, and with high-rise, it's going to be much easier to see this kind of thing and get a much better idea for at least some areas how these layers are formed. This shows an example of some cross-bedding units on the Earth. You can see I think that's a foot there that we're looking at for scale, at least not more than a yard. And how these formations form are they basically, the front of sand dunes, the wind carries the sand up over the edge of the dune, then it's deposited in the front of the dune. And you can see that these cross beds in here, and then another layer of sand coming in with a different wind depositional environment. And here's a zoom in of this picture of Mars, and you can see it looks a lot like this picture of Zion National Park. I remember standing and looking, I think, almost at the exact outcrop here. So it's a similar scale. Each of these layers are about 1 meter in thickness, and similarly right here. So, for geologists, this is extremely exciting that you can finally do roadside geology on Mars. It hasn't really been possible previously. So just being able to look at an image, you can get a much more detailed interpretation of what's going on. This falls into the category of something I just think is cool. I really wanted to throw in. This is Mojave Crater. It's on Mars. If you ever flown over the Mojave Desert, you'll agree that it looks just like this. It's a very well-named crater. This is a very unique feature. It occurs in a 60-kilometer diameter crater, and it has these beautifully preserved alluvial fans. The hypothesis about how this formed is that when the meteor comes in and hits the surface, it vaporizes water in the subsurface, and it causes a local system of rain to occur. And this is a really key question because we have these very large channels that you see on the surface of Mars that formed early on, and we think that one possibility is it may have rained out of the atmosphere, but it's possible that rain was actually caused by huge impacts. So investigating places like this are really important for understanding the history of water on early Mars. And this is a larger portion of this crater, and this little box shows you this inset here. One thing that's so important or so diagnostic about the morphology here is that you see these tops of these alluvial fans, these drainage ditches go all the way to the top of this peak. So it couldn't be groundwater just seeping out of the side of the wall like we see on many places on Mars. It really had to be precipitating down and raining in this area. Now, prior to high-rise, it was assumed that, this one crater was the only place this was known to happen. But high-rise has taken images of a number of other places of fairly young impacts, and they see similar evidence for these alluvial fans coming down from the tops of ridges. So apparently this phenomenon isn't quite as rare as we thought it was previously. Okay, so now I'm going to talk a little bit about the evidence of water from the minerals. And I'm guessing many of you have seen this picture. This is the landing site for Opportunity, and they were so fortunate to see these rocks at the first glance out from the rover when it landed. And on further investigation, they saw these sedimentary rocks containing sulfates. Sulfates in this form indicate the presence of liquid water in these minerals, and they saw these small blueberries in here. So this is one of the important pieces of evidence that minerals had been altered or formed in the presence of water. We saw a lot of evidence additionally from a spectrometer on the Mars Express, the European mission, and all these locations are in very old rocks from the first billion years or so of Mars history. The clays are formed in the earliest rocks, and the sulfates are kind of the next phase of water. So the clays require a lot of water to form. The sulfates not quite so much. So we went based on the evidence from the mineralogy so far, we went from a pretty wet place early on to a somewhat wet place to to a very dry place for the next 3 billion years. And here's the MRO view of this. This is the Opportunity crater and the lander inside here. And this is the picture of, sorry, that was Eagle crater, wasn't it? Sorry. This is Opportunity crater. This is the MRO view. And this is the zoom in on this little square here where you can see actually the rover on the surface from orbit. This is the view that the rover has of this crater from the surface. And just to show you some of the detail over here, here's the rim of the crater, and the rovers have been using the MRO data, and particularly the stereo data from MRO, to plan their traverse around this crater and plan where they're going to go up to these little points and take data back to look at the rocks exposed in the wall of the crater. And this is also one of those, this is just too cool not to put in. Here's the rover tracks that are, we were able to see from orbit on the edge of the crater. So we'll know exactly where it's been. I can't hide. Okay, this kind of illustrates the real value of having this suite of instruments operating at Mars together. Now the three imaging instruments can take data, or the three high-resolution imagers take data, often they take data at the same time. They're co-aligned. And this shows in the background is a high-rise image. You can see dunes in here, the whole series of dune fields, and then this rock exposed, and you can see the highly fractured rock down here. And on top of that is superimposed color, and that is based on the spectrometer data, which has been interpreted in terms of the minerals present. So what you can see in red is the olivine minerals, which is a mineral that's common in basalt. The green shows where clay minerals are formed. And now there had been evidence previously for clay minerals on the surface from the Mars Express mission. But what's really, really helpful in having this high-resolution data is that it really tells you the geologic context of where these minerals occur. Now, you can have olivine-rich rocks like basalt that can weather down and form clays. But that's not at all what we have going on in this situation. That might be what you would expect. But in fact, the olivine has come from far away. And one of the things that's very interesting they're seeing in this stratigraphy is that oftentimes the clays are in the bottom rock, the oldest rock that we see exposed. And frequently above that, you might see a layer that's olivine rich. Now, olivine is a mineral that breaks down in the presence of water very easily. So what that says is that you had a water-rich environment, things changed dramatically, and then on top of that, these olivine-rich rocks were exposed, and then there was no more water present in that olivine. So something changed quite dramatically, at least locally. Here is another example of the spectrometer data, and these are obviously all false colors showing highlighting different compositions and spectra. This is a infrared false color, and this is highlighting a particular band that highlights a particular mineral. And in general, what we have here are these very old Noachian layers lower down, which contain iron and magnesium-rich phyllosilicates or clays, and sometimes they also have aluminum-rich species. And the details of what minerals are in there tell you a little bit about the environment, whether it's warmer or colder. And then frequently there's an olivine-rich layer on top of that. Okay, so here's a little slice through the Noachian, the earliest history, exposed in one region. So in this dark-colored unit, we have the pre-existing rock, which has been weathered to these clay minerals, the phyllosilicates. In the next part, we have this olivine-rich layer that's in place but not altered, not exposed to water for long at all. And then subsequently an impact crater formed. It was filled by either melt formed during the impact itself or perhaps later volcanism. That's this dark unit here. And then a channel came in And here locally, we did have weathering of the olivine. So you can see that the environments change very dramatically in terms of their water content. Okay, now another way we can get at the history of water is to look at these old fractured rocks. And it's a very common phenomenon that you see on the Earth. In each of these cracks, we have some different processes going on which indicate that water flowed into these cracks. In this one, what you have is what's called bleaching. And you can see how these fractures are all a lot lighter. So somehow the water content, the minerals that were dissolved in the water that came in here reacted with the rock around it and caused a chemical reaction which lightened the rock. It can also go the opposite direction. You can end up having oxidation process which makes the rock darker. So you can see fractures in here where the surrounding rock was actually made darker. And then another process which can occur when water flows into faults is induration. So basically those faults were made, the chemical reaction, whatever it was that took place, made the faults stronger so that when later erosion occurs, they actually end up standing higher than the surrounding rock. So they're strengthened by the chemical reaction from the water. And those are all high-rise images of small-scale faulting. And here we're going to zoom in. This is Valles Marineris and the 3 volcanoes on Olympus Mons. So we're going to zoom in and take a look at some of the fractures in one of the offshoots here of Valles Marineris. So here's the whole piece of the high-rise image. So that part is 6 kilometers. And then we're going to be zooming in to look at some particular areas. In the center of the high-rise camera, there are several color bands. So in the middle of their images, they can get information about differences in composition, not specific compositions, but changes. So here's one of these faults that's been bleached out, and you can see a whole series of layers in here. This dark false color blue is basically the dust. So you see it forming in dunes, and then it lays along the layers as well and highlights those layers. But we'll see a series of these faults in here, these fractures through here that have caused, in general, have caused the rock to become lighter. And this looks like, I think it may be a more of an indurated fault where it's higher standing now. And these movies are really a great way to actually show the full resolution of these high-rise images, because it's really, I mean, there's no way it's possible on this one screen to show a single high-rise image at full resolution. But by having these movies, it allows us to scan through the image and see the full resolution, the full extent of the geology. And these were courtesy of Eric DeYoung here in the audience. I'm sure you've seen many of his movies here in the past. So it really gives you the ability to feel like you're standing on the edge of the Grand Canyon or something and looking down into these chasms and just seeing the extent of layers. These really show the incredibly long and geologically complex history that's gone on to form these craters, form these chasms. And we're still, in some places, there's evidence that some of these layers were modified by water, but they're probably the majority of the layers were put down through volcanic processes, probably mixed in with impact processes. Certainly not the whole extent of these crater walls were formed via water. So each of these is a very fine scale layer exposed in the chasm. So that one strip is just a kilometer across, half a mile. So you can easily, walk across it in 10, 20 minutes. Okay, so that was a little bit about the early history of Mars from HiRISE. And now I'm going to talk a little bit about the present day history, or present day activity. The first thing I'm going to show you is a little bit about the polar cap. And these are formed somewhere on the scale of millions to tens of millions of years. At least we think that's the case. They have a whole series of layers, probably forming in response to changes in climate due to the tilt of Mars' axis varying over time. The next thing we're going to look at are some evidence or some regions that have at high latitude that have near surface ice. And we don't know how long the age of that ice is. It probably interacts with the atmosphere in seasonal cycles, but it may have been persistent for much longer. We're going to see some gullies, which you may have heard about in the news. There's evidence for at least 2 of these being active within the last 7 years. And then we're going to see some fun features formed by CO2-related processes. On Mars, there's CO2 ice due to the low temperatures as well as water ice, and they form their own kind of unusual set of features. And then we'll talk a little bit about the weather on Mars. It's certainly highly variable, and we'll see some of the dunes that have changed over time due to changing winds, and some of the cloud and storm systems that can be seen on the surface, and go look at the change on just the daily cycle in the weather or in the temperatures seen in the atmosphere. Okay, so one of the things that MRO has focused on early on is the North Polar Cap. And we arrived in North Polar summer, so all the instruments were eager to observe there before it went into darkness. This shows the coverage from our context camera, our medium resolution camera. This traces the path of looking for a safe site for the Phoenix lander at about 65, 70 degrees north. And this just shows this coverage on the background image. These northern layer deposits are extremely beautiful features. They have a series of different units, the upper unit and this basal unit, which forms a steep cliff. These layers are believed to represent evidence of different climate change overall. As the layers are deposited, you have differing amounts of ice and dust recorded depending on the climate at that time. We'll see that with the suite of instruments, we're getting to a much better idea of their formation overall. One of the questions has been, how continuous are these layers? Do they really extend throughout the entire deposit or not? And this is just a lovely context image picture. It's 30 kilometers across. So you can see these layers are really huge in many cases and extend over a long area. They erode out at different rates. Some of them form steeper units than others. This is another context image. Here's a kilometer scale bar down here. And you can see that not all of the layers are continuous. Some of them, here's a continuous layer sitting on top. There are these discontinuous units. So they have a variety of different morphologies. Some of them have probably gotten eroded away, and then more layers deposited on top. This is a couple of the channels from the spectrometer, and it's superimposed on topography data, so you get a sense of this cliff here with the polar layer deposits on top, and then this basal unit on the bottom. This channel down here from the spectrometer indicates it is sensitive to the amount of ice. So you can see the scarp in the polar layer deposits is quite rich in ice. This steep cliff-forming unit has only very small chunks of ice, at least at the surface of it. We also get an idea of how the compositional units are related. Out here are big dune fields that were thought to be sands that erode out of these polar caps. And we can see is that these dunes in the foreground have a spectral signature similar to this upper basal unit. The lower unit is, as I said, mostly depleted in ice, and the spectrum for the dark basal unit is similar to the layers that are exposed in the top. Okay, so this is data taken by the ground-penetrating radar, and you can see it's on the edge of these polar caps. And what we believe that the radar is seeing, and this is it's kind of it's like a seismogram looking at the layers in the interior. We can see that the lower polar layer deposit has very kind of coarse layers, whereas the upper part of the polar layer deposit has very fine layers. So that's what we think is exposed in these what we call radargrams of the interior. So basically, each of these bright lines is a layer where the radar has reflected off that layer and sent a reflection back up to the spacecraft to be recorded. So we see these very fine-scale layers in the upper part, which are extremely continuous and, in fact, continue over much of the cap. And then this lower unit, which has fewer layers and more irregularity in them. This part down here is the base of that unit, and in fact, in this very cold, relatively pure ice, the radar can actually see down to a depth of 2 meters, so about 1.5 miles. So for the first time, we can actually know how thick these polar cap units are, and get a sense of their volume and the continuity of the layers throughout. And this shows a couple of, actually one pass through the deposits. This is Chasm Boreal, a big chasm that occurs in the polar cap. So you can see the fine scale layers for the top up here, and you can pick out layers that are continuous all the way through. Here's some zoom views of this upper part. So you can see many of these layers continuing all the way through. So it really says that a single process put down a layer of the entire region. This is bad. I can't believe that. Okay, so I'll speak more quickly, I think. No, I actually don't have a cable here. Sorry, I thought it was fully charged. I was expecting it to go for hours and hours. Thank you, Rich. Sorry. Okay, so here's a high-rise image, and so remember we're looking at a much finer scale, and the basal unit, as I said, is has much more massive layers, and it has this very blocky, fractured terrain. Sometimes you see the sand eroding out, and it forms these relatively steep cliffs. It's a very strong, hard to erode unit. This shows a section of the color data from HiRISE. This is obviously false color, but it goes all the way up to the polar layer deposits on top. You can see, again, these very fine scale layers in here. Okay, so this is another movie that will show us a little bit more some of the detail of these, skipped that, of the polar layer deposits in the HiRISE data. Oops, I guess I have to be more patient. I'm going to go back and go. Go back. Sorry, let me try this one more time. There we go. So here's the big chasm that we're looking at in the radar data, Chasm Boreal. And we're going to zoom in and look at one section of the wall of this chasm where the layers are exposed. So this, the orange colored material is more dust-rich. This white is frost on the surface. Thank you. Yeah, the newer one. Thank you. Sorry.
One moment, please.
Okay. Where do I pull this underneath? Okay. Oh yeah, thanks. Thank you. Thank you. Okay, so here's some of these beautiful layers. You see the sand coming out of many of them, and this highly fractured material in here. These small-scale fractures like that are probably formed as materials eroded away, and this material had once been covered by much more material that weighted it down and fractured it. And then we see the top of it, of the polar layer deposits. Again, you see a bunch of this sort of polygonally fractured terrain. Some places more prominently polygon shaped. Other places it's more irregular. So these polygons are, probably formed as moisture is lost, and it forms sort of a desiccated surface on the top, just like mud cracks in the desert, or cracks that are formed in permafrost in the earth. And here's a rare crater on these polar deposits. The reason we think that they're relatively young is that they have so few craters. But with the higher resolution data, we are starting to resolve more smaller craters, which should give us a better idea about the overall age. Okay, as I mentioned, that in the high latitude regions, there's evidence for ice in the soil, the regolith. This is data from Mars Odyssey, the gamma ray spectrometer, which is sensitive to water in the upper meter. So the next lander that's going to be launched actually in August is the Phoenix lander, and it's going to go to this high latitude region and try to dig into this near surface ice. This is a Themis image from Mars Odyssey. This was originally their prime candidate mission or location for landing, and but then as we got data from HiRISE that showed one of these dark areas, we learned that these dark spots are in fact 4 to 5 meter boulders, and that the rock coverage is over 50%. That began the campaign of looking for a new site for the Phoenix lander, and this is what a lot of the terrain now looks like in their primary landing site. And you can see that there's less than 5% rocks. You see very small isolated boulders out here, and these polygonal fractures all over the place. So this is a much happier looking landing site. Now you may have heard in the news recently about gullies that formed on Mars. This data was taken by the Mars Global Surveyor, which unfortunately now is no longer with us. But what they saw by taking data over many, many years is that these gully features, which may form through liquid water, they actually kept trying to observe them and find new ones, and finally they were able to find two. And this is this new deposit, which formed within, in this case, about 6 years. Now, HiRISE have certainly been going to follow up on these regions. And in the 15 months since the last MGS image was taken, there have been no changes in this area, but we'll certainly continue to look for evidence of new gullies. Now, this is a zoomed-in picture, and it shows that you see these very narrow tongues. This is just 10 meters down here for scale, which shows that it's a very fluid material. And it may actually be ripples in here. That's kind of at the limit of resolution. But there's a lot of conflicting evidence about how these really form. In some, the evidence seems to point towards water, but there is some contradictory evidence. Overall, the bright material that they see in their color data isn't consistent with frost. It has a very rough texture, and the new deposits maybe from erosion or deposition of actually bright material. In some cases, actually see local areas of bright material that appears to be eroding down to form the gullies. Here's a zoom in of a different gully. The white stuff is frost, and then there's frequently these smaller little dark channels. And it seems like these small channels are removing the seasonal frost and dust. And in these areas, in shadow, that material, this material that's eroding out and dark, it's too cold to be water. It may be CO2 in this area. And it may be that there are a variety of processes that actually contribute to form these gullies. I think I'm going to actually skip this one. Okay, so I'm going to just show you a few of these CO2 features. They're very unusual. Here's the whole image here, the high-rise image at 200 meters. There are these unusual kind of circular features that erode into the CO2 cap at the South Pole at the surface, and these have been seen over the past years to grow every year as they sublimate in the spring. And this is just the edge of one of these features that form as this frost melts in the spring. So HIROS is going to be monitoring these and trying to understand better the processes that form them. This is an area in a dune field in Russell Crater, fairly high latitude. And you can see this is a zoom in of this top of this dune right here. And you have these kind of little pock marks, this little kind of chicken skin texture in here, as well as these very narrow gullies that flow down the dune faces. Now in a dune, you're not going to have water coming up to the top of a dune field. So the hypothesis for how these form are that you have little bits of CO2 frost that get covered by dust, and then as as it gets more illumination from sunlight, the CO2 frost actually causes a little bit of explosion and shoots the dust up, and on the dune faces it allows stuff to erode down the side. So this is an example of a very different kind of gully that's been seen. And these are some geysers that have just recently been observed in MRO data. They're thought to form in a kind of similar process. So you have the ice cap here, and then as the sun comes in and heats up the top layer of this ice, if you have some CO2 that warms up down here and forms a gas, it makes a small explosion, and it brings up dust and whatever else to the surface, and the wind blows it and causes these little jets. It looks like little explosions on the surface, but it's the stuff being carried downwind. And we're actually trying to observe these at multiple angles and see if we can actually see in stereo the geysers coming up above the surface. Okay, here's an example of a dune field, which is showing different directions of dunes, showing that the wind has changed over time. Here's some cloud phenomenon. The weather on Mars is usually pretty predictable. Clouds such as these at the top of Olympus Mons tend to form around the same time every year. And here's an example of just lee wave clouds that form behind small topographic obstacles. This is the South Polar Cap, and you can see changes in the hazes and fog that form around the edge of the cap just over 2 hours. This is a storm system that's observed around the same time every year. So these dark sands underneath, the dark sands heat up, cause the atmosphere to rise and form these storm patterns pretty predictably every year. And here it is moving out away from the cap. That was in Marcy data. Okay, so this last movie shows you an idea of how the Mars Climate Sounder takes data of the atmosphere. This is a temperature scale going up to 200 degrees Kelvin. And you can see Mars turning underneath. So basically this is the pattern of the spacecraft as it moves around each orbit and samples the temperature in the atmosphere. So you can see this is the day side, the sunlit side, that's warmer. The side of Mars that's in the dark is cooler. You can see the cool atmosphere over the polar caps. And you can see that there's basically the spacecraft goes around Mars 13 times in a day. So it goes in about 30, changes about 30 degrees of latitude. So you can see those changes as the spacecraft goes over different latitudes around Mars. Okay, well, that was my last movie, and I hope I've whetted your appetite for more great data from MRO, and I'll take any questions. Yes.
Can you elaborate on the recent press release that, was it the northern polar ice cap that would melt? It would engulf the planet with liquid water?
Yeah. Actually, no, it wasn't. But it's from the radar data that's acquired on the Mars Express mission. And with that radar data, they estimated the volume of the polar cap. And they just extrapolated out what if that polar cap were to melt, how much water would be around the surface of Mars. And if I remember, it was about 10 meters. Is that right? I can't remember. I think it was
36 inches
yeah.
or something. But it's
maybe 1 to 10 meters, I guess.
That sounds like a significant amount of water
But as in comparison to an ocean, it's still a relatively small volume of water. And in addition to the evidence of possible evidence of past ocean, there's also isotopic data from the atmosphere, which basically the hydrogen to deuterium ratio, which it tells you how much water has escaped. And looking at that ratio, it says that it says that Mars once had a lot more water. So even though there is a significant amount in the polar cap, not a trivial amount, there still has got to be more that was around early on in the history, either still below the surface or in space. And actually, MRO, the radar data from that can also maybe get a slightly more accurate estimate of the polar cap, but it'll be very similar. Yes.
I take it all the water ice is in the northern polar cap. The southern polar cap is dry ice?
At the surface, it's carbon dioxide ice, but we know beneath that, the superficial layers of carbon dioxide, it's in fact water ice. And in part, that's because if it was just a giant layer of carbon dioxide ice, it couldn't keep that kind of steep topographic pattern. It would we know from laboratory experiments that the carbon dioxide ice would flow away and have a much more low profile. So in part, it's due to the topography. And actually, historically, there have been some years when the carbon dioxide ice actually melted away so that some water was exposed underneath. So there's kind of different lines of evidence that suggest that in the mass majority of the cap is ice, but with CO2 on the top. Yes?
In the early part of the talk, there was one strip that you were showing us, had a lot of blue that was false in color. There was a lot of white area, and I was wondering what that white, I think it was a rocky.
In the rocky image in the movie? Yeah, it was just light-colored rock, and I don't know exactly the composition of that rock, but when we have a chance to take the spectrometer data for that area and analyze it in terms of its mineral composition, we'll get a better idea, but I can't tell you the exact composition yet. Yes? Yes?
I noticed some pictures on the was named like Marcy. Is it nickname? Is it some frivolity? Like
it's let's see, Mars. What does it stand for? Mars. Thank you, thank you. Mars Color Imager. So it's an acronym. Yeah, that's what most of the names are, and I tend to use them so often I forget what they stand for. Yes.
What's the inclination of the orbit?
For MRO,
Yes.
it's 92 degrees.
So it's polar.
Yes, it is a polar orbit, yes. Mm-hmm. Yes.
I know that Mars doesn't have a whole lot of atmosphere, but isn't it rather dangerous to take them that low, those things that they could bump into the atmosphere and then go down?
Yeah, well, we've actually had a fair amount of experience flying spacecraft even at lower altitudes, because when they aerobrake, when they bring them in and start out with very elliptical orbits and then come down lower and lower until we get to the circular orbit, they actually go down to closer to 100 kilometers into the atmosphere. So even though they pass through rather quickly, from that past experience, we do have information on the density of the atmosphere and the changes in the density at those altitudes. So there was a lot of work that went into, mostly done by Rich, to try to determine how low an altitude was going to be safe. But one thing we weren't too sure about is how how good our predictions of where we're going to be would be, because as you go through the atmosphere and it changes, that changes your prediction, and you want to know where you're going to be, so can plan where to take your images. But in fact, it's actually turned out to be somewhat easier to predict what the atmosphere is going to be like at that altitude than we had anticipated. So it's worked out quite well. Yes?
What sort of velocity is required to keep it at that low orbit?
Well, let's see. Okay, basically it's about 3 kilometers a second is our velocity in the atmosphere.
How does that affect your high-resolution cameras as far as like shutter speed?
Well, it basically we take the data as we pass over it. So it's very much designed to match that speed. So it's not really it's a CCD camera. So the CCDs basically fly over the surface and are designed to read out at that rate to make the imaging stable. Yes?
Are there any large depressed areas on Mars which suggest that there may have been oceans there at one time?
Yeah, certainly in the topography, in the northern plains, there are areas that people have looked at image data and suggested they may be shorelines. So the northern plains are where an ocean may have occurred, but there's kind of conflicting evidence to support that claim or contradict that claim. So, I think the new information we're getting from HiRISE so far seems to contradict the ocean hypothesis in that there are boulders everywhere, which is not what you expect for an ocean. But I wouldn't say it's definitively no ocean yet.
How depressed are those areas?
Several kilometers, at least. I'd say maybe up to 3 kilometers.
So comparable to the oceans on Earth?
Somewhat shallower, but quite significant. Mm-hmm. Yes?
Would there be a groundwater? I know there's a lot of rock on Mars. Is there a groundwater there, or just in the poles or what?
Well, I wish I could answer that question definitively, but with these gullies, one of the hypotheses is that they form, they always form in cliff faces, frequently in impact craters. And so there may be fractures that allow aquifers, groundwater, to actually flow and break through sort of an ice dam at the surface of water. If sunlight comes in and heats that ice, one hypothesis is that there's aquifers that feed these jets of gullies that form these little narrow streams. So that's one hypothesis. Another is that it's more like deposits of frost or even snow that kind of sits on the side of the either at the top of the cliff or on the side of the cliff, and then it's exposed to sunlight that causes it to melt and form these gullies. So there are reasons to believe one versus another. Both processes may be operating, but we're trying to investigate that question. Yes.
Early on, Hellas was considered to be kind of an interesting feature. Have you been looking at that?
A little bit, yes. And one of the areas that's been looked at and has been proposed as a landing site is a crater that's kind of near the top of Hellas, and it appears to have been flooded by water at one point. And in fact, there's evidence of a major scale flood that ripped out big chunks of rock off the side of the wall. So there's some suggestion that maybe the whole area was filled with water at one time. But I'm sure we'll be looking more at that area. Yes.
Do you have any indication what kind of rock those boulders might be made of?
The ones I was just talking about? In that particular case, they are layered rock. So possibly earlier lake deposits, or, again, they could have been wind deposited rock. But in that case, it was definitely layers. But we don't yet have compositional identification of minerals in them yet. So, yeah. Yes.
Have the data from MRO settled any open questions?
That's a good question, and people never like to be pinned down to a given answer. But like I was saying about the oceans, I mean, it certainly suggests that it's not just water that dropped those sediments. It had to have been ice, something that carried all those boulders all over the place. So, could it have been a combination of processes? Possibly. I guess questions that it's definitely answered. In some cases, like those cross-bedded places, that was formed by wind. So we're starting to say, okay, here's something that was formed via this process. And I would say also, with some of the compositional information, this is rock that was altered to form a clay. So water was there for a long time. So, so we're getting some pieces of an answer, and, I think really it takes at least a year or two of taking all that data in. I mean, it's a big fire hose right now. And, we just had a conference and a bunch of the people were sick. They're just like, they're just so eager and overwhelmed to be looking at this data that it takes a while to ingest it and have enough perspective to stand back and say, from all of this data from all these different places, we can now really make this definitive statement. So it's kind of early on to have a big, grand, unified view yet from this. But certainly, some small scale questions, yes, we're beginning to get a definitive answer. And, but it's really the perspective of taking all the data in that will make us give us really big leaps in our understanding. Yes.
Have there been any indications of seismic activity? I saw a false scarp type of thing in the beginning of this, and I was wondering if that's seismic activity.
Yeah. It certainly was formed by an earthquake at one point. Those faults certainly formed early on, but there's, based on models, there's reason to think that there's still some activity ongoing. Almost every place has some seismic activity, although it's certainly not as active as the Earth because we have active plate tectonics, and most of the tectonics was happened a long time ago for Mars. But yeah, early on, they had a lot of faulting going on, and it was a very active place, but it's a little sleepier now from the faulting standpoint. Yes?
If you had layers, and you could have it, like a lot of water and then sand, but if you had sandstone, it'd take blowing sand and then a little bit of moisture, and then on top of each other would become rock that way.
Yeah. And in fact, that's the scenario that you would apply to that area which I showed cross beds. So yeah, I mean the sand is deposited and buried under kilometers and kilometers more, and that pressure causes it to be strengthened into rock over time. So. Yeah, certainly some of the layers are formed that way. Okay, I'll take one more.
Determine the interior temperatures.
I'm sorry?
Is it possible to determine the interior temperatures?
Well, we certainly know the temperature of the surface. And in terms of the interior, we can estimate the amount of heat coming out of the interior based on its composition. So, with some uncertainty, we can predict the temperature as it increases in the interior. We can predict the depth at which we expect water to be liquid and so forth with some uncertainty. So, yeah. All right, well, thanks for coming, and we'll hope to come back to more MRO talks.